Hi, so this video is going to be a walkthrough of my internship project. While I made the last video, I realized that it has more of a fun vibe to it, so I don't want to kill it entirely by adding a lot of technical stuff. So I thought I'd make a separate video on this. I interned at the MFRL lab at IIT Mandi, and my project was titled Neural Emulation of Gravity-Driven Geohazard Runout, and it was a replication of a research paper. So coming to the problem, why does runout prediction even matter? So about 17% of land area is affected by landslides, and about 8% of global population lives in these potential runout zones. And problems like climate change and accelerating urbanization are only fueling to this. Now, the core challenge that we face is that in case of such an event, the emergency responders need runout estimates within minutes and not hours after a triggering event. And the reality is that the traditional physics-based solvers take at least 10 to 200 seconds to run per simulation, making them impractical. So talking about the traditional approaches, we've got the empirical and the statistical approach, which basically use the past data to analyze the travel angle, which is the horizontal flow and the vertical drop. But the only problem is that it does not take into account any real physics, so like no real physics equations or anything involved. And the second is using physics-based solvers and simulators like Flow, but the problem we face is that they are very slow. So the solution to this was neural emulation, that we train a neural network to imitate the physics solver, and as the paper stated, that it was found that it was around 1000x times faster than basically a traditional solver. Now, the paper that I reproduced, titled Neural Emulation of Gravity-Driven Geohazard Runout by Lorenzo Nava et al., they made available the model architecture, the inference utilities, their pre-trained weights, and their dataset of about 90,000 NPZ files. But what they didn't release was the training script, the loss function, and the exact training configuration. Now, let's talk about the model architecture. So we use something called UNets. Now UNet was originally proposed in 2015 for biosegmentation, and this is how it looks like. So these are the 4 encoder blocks, and this is the bottleneck, and then these are the 4 decoder blocks. And the gray arrows that you see here from encoder to decoder blocks, they are called the skip connections. So basically UNet is an encoder-decoder architecture that was originally built for image segmentation. And the encoder progressively downsamples the input image, and it increasingly extracts more abstract features, and then the decoder progressively upsamples it back to the original resolution. So basically it reconstructs a detailed output. Now, what makes UNets work so well and basically so unique? It is the skip connections, because at each resolution level at the encoder, the features are passed directly across the corresponding decoder level when it's being upsampled. So whatever fine spatial details are lost during downsampling going to the bottleneck, they can be recovered back while upsampling in the decoder stage. So for this project, I use a slightly modified version of UNet with a few additional features. So the first one, the convolution blocks. So in a standard UNet, you've got plain convolution and batch normalization, and ReLU stacked twice in each encoder block. But in this project, we use residual convolution blocks, basically based on ResNet. So we got convolution, group normalization instead of batch normalization, ReLU and dropout, and then again convolution and group normalization, and then we have the input added back, which is a classic property of the residual convolution, ResNet. And then we have ReLU. Now, why did we do so? So residual connections ease gradient flow in deeper networks, and we use group norm instead of batch norm because it is more stable for small batch sizes, like here we have 8. And dropout is basically a regularization technique which just prevents overfitting, basically reduces dependence. Now second component is that we conditioning on scalar parameters. So here at every encoder block, we are basically injecting 3 scalar parameters that all our samples depend on, that are density, cohesion and volume. And standard UNet, there is no such feature, no such mechanism to incorporate these, but in this project we use something called film, which is feature-wise linear modulation. So at all 4 encoder stages, there was conditioning on cohesion, density and volume. And why so? Because landslide runout depends on heavily on the material properties, right, and not just the terrain, the DEM. And film helps us, handle many material scenarios instead of just training separate models per parameter set. So instead of making a separately different model just for this, we could incorporate this also in this modified unit architecture. So coming to the next component, which are the skip connections. So in the image we saw earlier, we saw that the gray arrows go directly from the encoder to the decoder, and basically that is direct concatenation of the encoder features into the decoder without any filtering. But here in this project we have the attention gated skip connections, where basically the encoder features are reweighed by a learned attention map before concatenation. So this basically helps the network suppress the non-relevant terrain information and emphasize on the likely flow regions of the runout, right? So improving the decoder focus. So the next component is the input channels. In a standard unit, typically we have 1 to 3 channels as input, so like a grayscale image or an RGB image. But here in this project, we have 8 channels as our input. So these are the DEM, slope, curvature, etc. And why did we do so? Because the network isn't learning from the pixels alone. So we have given additional information like the hydrology and the geomorphology informed features directly as the input. Next component is the output. So in a standard unit, we get a single output head, that is one image, one segmentation mask, right? But in this we have dual heads, so we're getting a segmentation of the probabilistic runout, and then we also have the final debris thickness. Typically in a unit, we have a single loss function, that is binary cross entropy for segmentation. But in this project, we have used binary cross entropy with dice for segmentation, and we have masked L1 for thickness. So why so? Because dice loss addresses the class imbalance, because landslide affected pixels are a small minority in the large entire image, and mask L1 avoids penalizing the thickness error outside of the actual runout extent. Now this is the entire structure, the architecture of the modified unit that we used. So let's talk about this in detail, zooming into every stage of this. These are the 8 channels visualized that we give in as the input. So the first channel is the DEM, that stands for a digital elevation model, and it basically contains information about the elevation at each pixel, and it is normalized between the range of 0 to 1. Then the second is the slope, which is basically about the steepness at each pixel, derived from the DEM. The third is the curvature, basically how the terrain bends, whether it's concave or convex. The fourth and fifth channels are the north-south and the west-east coordinates. So it is basically positional, relative position within the patch. So in our case, it's like a 256 by 256 image grid. So that. Then we have the flow accumulation. So it basically uses the D8 algorithm to highlight the likely, valleys and channels where deposition can happen. So if there's a valley, it'll have a high value. Then 7th channel is distance to source, which is basically distance of each pixel from the source point of the landslide or avalanche. And the 8th channel is the initial thickness, that is H0. So the thickness at the source point of the avalanche or again landslide, and basically all values except that small area for of that source point will be 0. So here we see the 4 encoder blocks and the bottleneck. So each encoder stage, so we pass to the stage 1, we pass 256 by 256 by 8 is the input, 8 meaning the channels, and with each encoder block as it goes down to the bottleneck, the image size shrinks and the number of features increases, so number of channels increases. So in each block we've basically got a residual convolution block. So we've got 3 by 3 convolution, 3 by 3 is the size of the kernel. Then we've got group normalization of batch size 8, then ReLU. Then the output of this gets passed down and to the dropout. And here p greater than 0.2 means each pixel will be assigned a value between 0 to 1. And if the value is greater than 0.2, it gets to stay. But if it's less than that, then it will vanish. And this is basically a regularization technique to help prevent overfitting. Then again it gets passed down to this block where we have 3 by 3 convolution, group norm and ReLU, and then finally comes to the addition block. So this that you see over here is basically a classic feature of the ResNet, where the input is added back to the output. This basically helps prevent vanishing gradient problem in deeper networks. And then we've got the film conditioning, so that we talked about, feature-wise linear modulation. We will talk about it later. And then after each encoder block, we've got the max pool, the pooling. The kernel size is 2 by 2 here. So this is basically a tabular representation of how the encoder basically progressively downsamples the image while increasing the number of channels with each stage. And finally, when we pass the input to the bottleneck, the image size is 16 by 16 and the number of channels is 512. Now the second input we have here are the global flow parameters that we pass as the input to the each film block in each encoder block, right? So film, the feature-wise linear modulation. So we have the three parameters that are the cohesion, density and volume, and they are passed in all four encoder blocks, right? Now coming to the attention gated skip connections. So the red arrows here represent the attention gated skip connections, and as you can see, they come out from the encoder block and they go to the attention gate first before they get passed down to the decoder. So talking about the attention gate, G here stands for the gating signal and it is coming from the decoder. Now the decoder has seen a more processed representation of the image because it comes from the bottleneck, right? It starts from the bottleneck and upwards, so it has seen channels and the more abstract features compared to the encoder at that point, right? And X here is the raw encoder skip features at that same resolution. So the effect is that the network learns to suppress this, irrelevant or the noisy encoder regions and then emphasize on the more spatially relevant regions, which are basically close to the flow path or the runout extent, right? Before blindly merging everything together, from the encoder to the decoder. Now this is how the decoder part looks like. So let's zoom into each block. So at each decoder stage, we've got a transpose convolution, so which is basically the opposite of convolution. And here the kernel size is 2 by 2 and the stride is 2, which is to upsample the image back to the original resolution. And it concatenates the attention gated encoder features to the corresponding decoder stage. And then it passes through another residual convolution block, which is like the same that we saw earlier in the encoder, or the same dropout, group norm, that same structure. So this is how the image progressively gets upsampled back to its original resolution. We can see how it progresses with each decoder block. The final output that we get in the last decoder stage is 256 by 256 by 32, and before we finally produce the output, we've got a one-on-one convolution which gets it back to the original size, that is 256 by 256 by 1. And these are the test results. Basically, we tested them on the test dataset NPZ files, and these are the outputs that we got. So you can see that it is pretty close to the ground truth, the predicted path. So here we've got good IOU scores, good F1 scores, and IOU stands for intersection over union. These are the test cases from Alaska, Asia, Australia and the Sumatra patch. Now talking about the loss functions, so as mentioned earlier, for segmentation we used BCE and DICE together, and for thickness we used masked L1. So the total loss is computed by adding all of these together. For segmentation, BCE basically measures how well the predicted probabilities match the true binary mask pixel by pixel, and DICE loss measures the overall overlap between the predicted and the true masks, which helps a lot when the landslide affected pixels, like the positive class as we call it, are a small minority in the total image. For the thickness loss, we used masked L1, which is basically mean absolute error, rather than L2, that is mean square error. Why? Because L1 is less sensitive to outliers or extreme thickness values, and masked here means that the loss is only computed within the actual runout extent, because there is no point penalizing the thickness prediction error, which is outside the landslide anyway, right? And L1 treats every error equally, so loss scales linearly within the error size, while L2 will square the error, so it punishes the large errors disproportionately harder than small ones. So the model was trained for up to 460 epochs, and here are the final training results. So the final training loss was 1.1116, the final validation loss was 1.3224, But the best validation loss we received was at epoch 204, which was 1.3222. And you can see here the learning rate dynamics. So by epoch 200 it kind of plateaued. Now here are the results comparison from the original paper. So their F1 score was given as 0.91, stated as 0.91, and our model was an average of 0.832, and IOU was 0.84, and for us it was 0.728, and RMSE was 1.60, and for us it was 2.65, which are kind of okay because they trained their model for 500 epochs and ours was for 460 epochs. Okay, so conclusions. So everything that I accomplished there, so I reproduced the UNAT Film Plus architecture from their published description from scratch, basically built the complete training and evaluation pipeline, and along the way identified and fixed whatever implementation issues. So finally trained the model for up to 460 epochs with stable loss curves. And future work that can be done on this is that we use neural operators for scale independent emulation, and we also include some sort of temporal analysis predictions and not just show the final state, so we can show how it progresses with time. And something else that could be done is multi-hazard extensions, so not just landslides, not just avalanches, but also pyroclastic flows that are from volcanoes, all of that. So this pretty much sums up my entire project. I hope I didn't bore you out there. And again, huge shout out to my professor and my mentors at the lab. So yeah, that's it for this video. Thank you so much for watching.